Okay, good morning, everybody. We ready to get started?
Yeah.
I think there's one more student that's going to join us. He was pretty excited about the class. One thing that's really different, I'm excited about this class. I've taught this class 4 or 5 times, I'm losing track, something like that. But I'm excited about this semester because we have colleagues in Anderson that are studying with us. So I'm responsible for this class in New Albany and a distance section in Anderson, Indiana. The course is also being offered on main campus in West Lafayette, being taught by Henry Zhang there, and in Columbus, which is being taught by a limited term lecturer, Mohammed Ashraf, I think is how you say his last name. Super great guy, I've met with him, and he and I are going to work closely in the course content. However, I'm responsible for the New Albany and Anderson students, he's responsible for the Columbus students. It's kind of weird, I feel sorry for the Anderson students, let me apologize to you ahead of time. The way it worked out, the class time matches Columbus and Anderson, and so Muhammad is delivering the lectures to Anderson in real time because we felt like that would be beneficial. However, these videos will be posted for the Anderson students, and of course, New Albany students, you can look at them as well if you want. This class is not a class where I do a whole lot of talking, a whole lot of lecturing. This is very much a lab-based class. And so we're not sure how that's going to work for a distance situation. And so please bear with us. I will tell you most students get out of this class with a pretty good grade, because your grade is based more on how much you work than anything else. And there's just a lot of work to be done in this class. It's very lab and project oriented. So I hope you enjoy it. I hope you like it. It's an area I really like. For the sake, let's see, all of you guys here know me, so I don't need to go through my background. I'll do that with the Anderson students during the lab on Wednesday. Okay, New Albany students, you don't have a lab on Wednesday. We're meeting Tuesday, Thursday, but the Anderson students are meeting Monday, Wednesday. And I'm going to WebEx in with them for their lab. All right, let's explore the Blackboard site. If you don't have access to Blackboard, you need to make sure and get access to it. I use it extensively. There is a book for the course that is recommended but not required. And here it is, there's the ISBN number. There is a paperback version, which I think is an international version. It may be worth picking it up, although we're not going to use the book a whole lot in the class. So it's your choice whether or not you get it. There are several mechatronics books out there, and most of them focus on signal processing and measurement, which is an important part of mechatronics, but it's certainly not the entire field. My background, as most of you know here, is in robotics, and so I lean more heavily toward motion control, and so that's how I've structured the course. If you look at the course website on Blackboard, you'll see the syllabus, my schedule, and a learning module already up, as well as some videos, some examples, and other things. What we do in this class is we use the Arduino platform for all of the programming we do and for control, and a whole lot of interfacing. So if you don't understand Arduino, that's okay. I'm going to help you through Arduino coding, but you'll have to pick it up fairly quickly. I don't spend a lot of time on Arduino coding. All right, so all of you should have had a programming language by this point in time. And so picking it up shouldn't be bad, especially if you've studied anything that's like C. Java is fairly close to C, although in Arduino you can have object-oriented code, a lot of it's more functional based. Okay, so if you know what that means, great. If you don't worry about it. I'll help you learn Arduino. All the examples that I make, because I do a lot of coding and show you, hey, let's make this program that does X, Y, Z, and I make it, you see it. All of that coding I post in the in-class examples. You can look at it now if you want. It's a little bit of a mess. I need to clean it up a little bit, so I'm going to do that. And probably what I'll do is move most of what's in there right now into a folder that's past classes. You can still access it if you want. But as I create examples, I'll add them into that area and make it more clear, so you'll know exactly where all the things come from. This writing lecture presentation we'll get into later. I will have you write some things, but let's talk about the course first. There are a couple of videos that I've posted. I want you to go ahead and start thinking about the final project, and we'll talk more about this in a little bit, but if you want to watch these 2 videos at your leisure, probably not while I'm talking, feel free to do so. And any ideas you have that you would like to create for a project, I would be interested in knowing about. So before we get into the course topics, let me run through the syllabus quickly, and this should be valuable for the Anderson students as well. Here's my contact information, and of course it's available on Blackboard. Office phone number is the best way to reach me, because in my office my cell phone doesn't work very well.
We are meeting here in New Albany Tuesday, Thursday, 9 to 11. Anderson is meeting 3:30 to 5:20 on Monday, and Wednesday 4:30 to 6:20. And I apologize, I don't know the location, I just know there's a lecture room and an electronics lab. I visited Anderson and met Corey Sharp, the director there, as well as Matt Blessing, who is the lab assistant that's going to, I don't think that's his correct title, but anyway, he's going to be helping out with the labs. And then Corey is helping us get together whatever we need to make the course hopefully work well for the Anderson students. You can read the course objective if you want. I don't know that I want to go through that right now, but basically we're going to study mechatronics with a hands-on approach. That's what we're going to do. Required text, you don't have to buy anything. The way that your grading works, the homework and laboratory is 20% of your grade, projects are 40% of your grade, and the exams will be 40% of your grade. There will be 2 exams, one in the middle of the semester and one at the end. Hopefully you like that. It's not 4 exams like I usually have in thermo. The distinction between the laboratory and projects may become a little bit blurred in your mind, because at first, really the laboratory is what I'm calling the first few exercises in the Arduino coding. Okay, after that, the lab exercises become so big I call them projects instead. Okay, so a lot of this grade is the final project, but there are smaller projects along the way that will count toward that. Okay? So you can see that 60% of your grade is coming from the work that you do in the class. So hopefully that will help your grade. When you're done, you should be able to do all the things listed here. And then there's other policies that are fairly brief. This does not affect the Anderson students, but we follow IUS schedule here, and if weather causes them to close, then we close also. I do give you tests, and you can look at them when they're done. Sometimes there's a paper portion, well, most of the time it's a paper portion and a portion on Blackboard. Okay, obviously you can go and review the Blackboard portion anytime you wish, but the paper portion I recollect because I do a lot of ABET measurements to make sure that I'm meeting all of these criteria here. Okay, so what else? The final exam may be comprehensive. It usually is not, but it does build on past things. Okay, so to say it's comprehensive is probably more accurate, but it's not intentionally comprehensive. Please don't cheat in the course. I really don't like it when students cheat. Try to give you as much help as I can. And I'm more interested in you learning than anything. So do your best to learn, and I'll be happy with you and give you a good grade. If you want to connect with me, you can do so now on LinkedIn, but I don't accept Facebook friend requests until after you've graduated. That's just a policy I put in place. I don't want you to feel like my personal life has affected your grades somehow, okay? But please, after you graduate, definitely look me up on Facebook. I'd love to connect with you there. If you don't want to, that's fine. LinkedIn is good too. I would suggest connecting with me on LinkedIn. I know a lot of people, and it's becoming a nice little network. So hopefully it will help you. That's my goal with it. Questions so far on the syllabus and what you need to do to get a grade in this class? I have posted my schedule, and I am, hopefully you guys know, but for the sake of the Anderson students, I'm always willing to get with you. Okay, I want to help you. I want you to learn. And so the hours I have listed here are not the only hours that I'm available. I've come here before in the New Albany site and opened up the lab for students on a Sunday because they needed to get their go-kart out and machine elements. I'm glad to do those things. I'm glad to meet with you after. There are certain constraints in my schedule I have no control over. I drop my daughter off, as most of you know, at about 8:30 at her school, and I come here and have classes at 9 o'clock Monday through Thursday. I pick her up at about 3:10, so I can't be around during that time. I have to be there to pick her up. But I'm glad to come back here, and sometimes she has to sit in my office, and that's okay. I've got coloring books and toys and whatever she wants there. So I don't mind meeting with you after 5. That's really not a problem. It's just most students really don't want to. Also, I do try to go home on Friday at about 3 after I pick her up, but if you want to meet with me, I certainly would be happy to. That's not a problem. Okay? I really like what I do here. I like this topic, not just mechatronics. I like all of mechanical engineering. So I enjoy what I do, and I'm glad to help you. So there's my course schedule. I've got the Anderson lab here. I'll put the correct room number once I know it there, but of course it's in Anderson, Indiana, not here. I do plan to travel. I hope to travel to Anderson on a couple of Fridays
to meet in person with the students there, though they don't have a class time schedule. We'll see if they want to or not. I don't know if they want to come in on a Friday to actually meet me, but I'd like to meet them. What else? I don't think there's anything else about my schedule. Questions, comments so far? Okay. If not, then let's go. Let me mention one more thing. This is the way that you see the course, the way it looks now on Blackboard. Let me turn off student view and turn on editing mode. There's a lot more in the course, and what I'm going to do is turn on more and more learning modules as we go along. I try not to inundate you with information, so I don't show you those initially or have them on initially, so that hopefully you're not overwhelmed by the course content. However, in the learning modules, I prefer my view, and I wish that I could give you the same view I have in the learning modules, but I haven't figured out a way to do that. All right, let's start with the presentation, which is pretty quick. And we will get into a hands-on exercise quite rapidly. What's happened to the clicker? I'll have to click the keyboard. All right, so my name is Damon Sisk, and for the Anderson students, I will give you a little bit more information about who I am, what I've done, when I meet with you via WebEx on Wednesday. But let's start off talking about mechatronic systems. Mechatronics is a term that's difficult to define. There's actually been several definitions of it over the years. We're going to have a sort of working definition or an understanding of what this is. But here are several different systems that actually explain or are examples of mechatronic systems. The Predator drum is certainly a mechatronic system. My car is not this new. My car is the old version of this car, but even this car and my car use a gas pedal that is called drive-by-wire. It's not like my steering wheel is drive-by-wire, okay? My steering wheel signals don't go to a computer somewhere, that would be dangerous, but my gas pedal position does. And even though it's a 2001, which is a fairly old car, the reason for it is that it's a diesel, number one. Now, you guys know how the diesel trucks work, right? Somebody's on your tail, no problem, you just hit the gas or hit the diesel, black smoke comes out and they back off your tail, right? Magic. Well, my car is supposed to be efficient. When you dump diesel into the engine like that, it's not really burned completely. You can tell because there's black smoke coming out. So it doesn't, you're paying money to put black smoke out of the vehicle instead of pushing the vehicle forward down the road, okay? When Volkswagen designed my car, they didn't want it to be that way. They wanted it to be as efficient as possible. And so they knew there's a point where you can give the engine too much diesel fuel, it won't be burned, it'll be wasteful, so why do that? So basically the way it works is the gas pedal moves a rotating, it's not just a variable resistor, but you can think of it as that, a potentiometer, and that sensor sends a signal to the computer requesting essentially an amount of power output or an amount of speed, okay? Or a throttle position is the way you can think of it. There's no throttle in my car. In reality, there's an injector pump, and the injector pump is well, there is a throttle that controls airflow, but the two things work together so that you hopefully maintain efficiency. Okay? So the computer decides based on the gas pedal position and I guess probably the speed of the car, how much diesel can actually be put into the engine to be useful. Okay? I like that. I also like the fact that now that I've got my turbocharger working, it does blow a little black smoke. So you can surprise people. If somebody's on your tail, you actually can give them a little puff of smoke and surprise them. But it looks funny coming out of the little Volkswagen Jetta. But this is an example of a mechatronic system. Well, how on earth are these two things that are pretty exotic and pretty common, how are they both mechatronic systems? Here's the key to mechatronics. This is how we're going to think about it. You need smart control. That means computer control, essentially. Okay, you need a microprocessor in there. There needs to be some sort of algorithm programmed into the microprocessor and memory where the computer is making decisions to control a precise mechanical device. Now you may say, well, I can see how the drone is a precise mechanical device because when you fire a missile or something, you probably have to aim it fairly accurately. Okay, so basically it's computer control of a precise munition. And I'm sure there are elements within the drone itself that also have to be very precise. Okay, the remote control is not really what makes this mechatronic.
What makes it mechatronic is the fact that it's a computer-controlled, precise mechanical system. So is this gas pedal thing that I just described to you, the sensor for pedal position is actually fairly fine resolution, okay? But really, that's not the part that makes it mechatronic. The fact that makes it mechatronic is that there is an injector pump on these cars, and by the way, I shouldn't make recommendations on camera, but I don't really recommend the Jetta, okay? I drive one because I rebuilt the engine in it, but there's an injector pump that costs about $1,000 to rebuild, and you need to rebuild it about every 100,000 miles, or it locks up, takes the timing belt out with it, destroys the head, impacts the cylinders, and now you've got a big expensive mess on your hands. Okay, that actually happened in my car. The injector pump locked up. That's why I know about it. Now, if you maintain your belt and you maintain your pump, it's not going to happen to you. They're fairly reliable. But the reason mine messed up is because some other owner before me had changed it from an electronic pump to a mechanical pump, and it messed with it apparently and didn't do it right, and it locked up. But anyway, the reason this is oh, by the way, if you want to buy a VW product and you want a diesel that's fairly high mileage, because mine's nice. I get about 45 to 50 miles per gallon. That's why I keep it around, okay? It looks ugly, but I don't care what you think, right? I don't have to pay out the wazoo for the fuel. If you want something like this that gets good fuel economy and is actually a little more comfortable, I would recommend the Passat. It's much more bulletproof. That's what I'm working on getting as a Passat. So I'll get one someday. It's not a real high priority. Why is this mechatronic? That injector pump has to inject a very precise quantity of fuel into the cylinder, okay? Not only that, but the throttle position that allows air in has to be fairly precise. So the mechanical side that the computer is controlling is precise. There's a lot of precision there. And so that qualifies this, in my opinion, as a mechatronic system. And here's a little more detail where you can see the actuator separated from the accelerator, so you can see the sensor that's determining the accelerator position. Here's some other mechatronic systems. This one's really old. Anybody ever used one of these before? Nobody uses these anymore. How old is it?
Betamax?
I think it is Betamax. I looked, when I was a kid, we had a VCR, and I thought I would include this instead. It's mechatronic. Why is it mechatronic? Because it's intelligent control. Well, maybe not this one. This one's pretty old. But VCRs became programmable. They had computers inside of them. And you had to precisely control the head position so that you read what was on the tape. See, the tape, as it went along, it was fairly thick tape, but the information wasn't just linear on the tape. It was actually at an angle. So if you ever look inside of a VCR, the head would spin, but it was tilted at an angle. And the reason for that is so that it could read successive elements of the track. And you had something called tracking you could adjust, that it just got that head lined up precisely with the tape, so that qualifies it, in my opinion, as a mechatronic system. There would be people out there that would argue the other way. Okay, mechatronics, and the term, is not actually nailed down all that well. The definition has sort of evolved over time, and different people have a different opinion about it. So I'm just telling you what I think mechatronics is. And I think it's fairly close. It's something that Professor Zhang and I agreed on. When we began this course, we designed it. He was on main campus and I was here. We're both mechatronics experts, and so we designed the course and we agreed on this as a definition. So anyway, here's another mechatronic system. We really don't use these a whole lot anymore. We still have one hanging up there. But if you ever take one of these apart, you know what's inside these projectors? It's kind of interesting. There's a color wheel. And the way it works is the image is projected through that color wheel. But you have to change the image for each color, because there's red, green, and blue that needs to be projected onto the board or whatever you're projecting the image onto. And so there's actually a color wheel that rotates very fast. In fact, what usually fails in these, and I know by experience, I fixed a couple of them, is the color wheel. The way they made these is I don't know if it's glass or what it is, but it's different colored lenses. They're actually glued together to form a wheel, and the wheel spins very fast. So what happens is eventually it goes off balance and the wheel just literally blows apart. It just shatters. At least in this particular model, which is why I chose it. This Mitsubishi, which is the same one we have up there. Anyway, what's interesting about this is that it basically is a computer. It has a computer inside of it, and it has to project the red version of the image, the green, and then the blue at the exact right time. So it has to know precisely mechanically where the color wheel is. Okay. So here's a little bit more information. This is the color filter essentially. There's our light source that sends light through to project the red portion of the image. And then there's a device that forms the image and then a projection lens for the image. So in reality, what's happening is it's flashing the red portion, the green portion, the blue portion onto the screen very fast, and your eye can't pick up the fact that the image is actually changing. Okay, your eye just sees it all together as one. Here's another mechatronic system. This is a laser printer. Okay, so what happens, we've got a laser scanning unit. In fact, I think I've got one. No, I had one laying over here. I bet I put it over there. Tried to clean up the classroom over the semester, or over the summer. I'll pull it out in a little bit, I guess, and see if we can look at it. But basically, you have a laser source and you've got a mirror. What's interesting about, in fact, you know what, let me go look and see if I can find that quickly. What's interesting about this is that the mirror, I think I put it over here, the mirror spins really fast. Yeah, here we go. I took this one out of an old printer I had. Let me take it over to the camera, and then I'll pass it around so everybody can see it. I've gone ahead and started to disassemble this, but basically this is the laser source. It sits in here kind of like that, and it shines a laser beam to this rotating wheel here. Now, if you probably can't see it on the camera, but each side of this wheel has a very highly polished surface, so it acts as a mirror. And then that way the laser beam can be scanned across this optic here and then shine out onto the page. So let me pass this around, you guys can look at it. What's interesting about that, you'll notice there's a chip on it, and that chip is a motion control chip. So what it's doing is it's keeping track of exactly where that motor is, and so exactly what the angle of the mirror is, so that you know exactly where on the page the beam is located. Okay? And the idea is that that laser is pulsed in order to create the image on the photoreceptor drum. So it's really interesting, because if you want precise text and things, you have to know exactly where that laser beam is. And so that's a mechatronic system. It's a computer-controlled precision mechanical system. Oh, I forgot I inserted an image of one here. That's the same thing as what I'm passing around. I didn't take this one apart. You'll notice it's interesting. It's the exact same chip as what's on that unit. Industrial mechatronic systems. Robots are actually a subset of mechatronics. Robots are an example of a mechatronic system. Robots are complicated enough, they deserve their own field, and of course they have it, but they are precision electromechanical systems that are controlled by computers, so they qualify. Anybody ever seen a device like this? Probably not, but you've probably used the products that this industry produces. This is a roll-to-roll machine. I don't know exactly what it's for. There's many different types, but there's a whole industry out there that you use probably every day and don't even realize, called the converting industry. The converting industry it could also be called packaging, because when you go to the grocery store, you don't actually see food, you see packaging, right, for the most part. And so that packaging has to start off life as either plastic or cardboard usually, right, and be formed into a package that contains the food and keeps the food from going stale. So there are tons of machines, sort of like this and many other flavors, that create the packaging and put the food inside so that it can be kept and stored and sent to the grocery store. Okay? These are mechatronic systems. They are computer controlled, and they're actually very fast, but they have to be very precise mechanically. Okay? So if you want to print onto boxes as they're going by, did you know that boxes are also printed with multiple colors? Those colors have to line up perfectly or else the image looks bad. Okay, so these are also, and also cutting the films and things at the right place is something that has to be done very precisely. So there are many examples of mechatronic systems in the converting industry. Here's a mechatronic system I designed for Grody. I've told you guys, and I'll tell the Anderson students about this when I see you on Wednesday, but I've told you guys a little bit about the light strips that I was involved in making for Grody. Well, the problem was we had this sandwich, basically, this upper and lower layer sandwich of plastic with hot melt glue in between. It was only about 30 thousandths of an inch thick, about a ½ inch wide, about a foot long. The problem was if water crept into the side of that sandwich and got in where the glue was, it would actually cause the product to degrade and the light wouldn't come on. So what we wanted to do was seal it. Think about a sandwich and putting plastic wrap around the sides of it. That's basically what we're doing. But we wanted to do it with tape. Okay, so we wanted to take this thin flat light producing device, wrap it with tape so that it was sealed. That's what this machine is designed to do. There's my Pro E version of the model, and there's the model, or the unit as it was being built. But basically what it does is it takes in the flat lamp here. There's a roll of tape mounted here and some, there's a couple of things. There's some tensioning and things going on here for control. I don't remember exactly how I designed it to wrap and why, but it comes back around and basically is married with the lamp itself here, stuck to one side and then rolled over the edges of the lamp, if that makes any sense. Okay. The rolling, most people thought that would be the hard part. That was actually the easy part. I designed a custom tool here that basically just, as the lamp went in, it was actually bent a little bit, and the sides went up to fold the tape around all in one motion. It worked really well. And there's a pinch roller then to just pinch the tape on top and connect it all. The hard part was actually the fact that each of these lamps were going to be fed in by hand. We wanted it set up so when you fed in a lamp, it just, applied the tape and sent it out and was ready for the next one. So how do you keep hold of the tape that has to be attached to the lamp and yet have it again once you cut it for the next lamp that's inserted? Okay, that's not an easy problem. But the way I designed this was to actually slice the tape as it was moving. So this was put at the right angle, and this is actually a razor blade being held at a slight angle, so that as it's going by, you can slice the tape very quickly, and then you're ready for the next lamp. So there's actually a lot of details. I've forgotten about this. I've done a lot of machine design, and this is just one of many. I need to sit down and figure it out again because I don't remember everything about how I did it. But it was neat, and it worked just fine. So anyway, why is it mechatronic? It's because it was going to be controlled by a PLC. So there's your computer component. And this was all fairly precise in order to control what was it? I know what it was. On either end of the lamp, there were contact points, and you couldn't have tape on those contact points. So we had to have a certain setback that had to be precisely controlled, and this machine was capable of doing it. So, all right, mechatronic system overview. A mechatronic system consists of several pieces and works together as this diagram shows. Basically, you've got the mechanical structure in the body of the thing, whatever it is. Okay, in the case of a printer or a robot or that system I designed, it's got a mechanical frame, mechanical components. There's a microprocessor and control logic or laws and drives. So these are the program and the brain of the device. Okay? The drives, I don't know how to describe this very easily. You'll understand it better as we go through the course, but basically you can't take an Arduino's output pin and connect it to anything directly, for the most part. It can drive an LED, which is a very small power draw, but you can't, for example, turn on a large motor with an Arduino directly. You have to have something in between the motor and the Arduino in order to amplify, okay, the effect of the Arduino. If you've used Arduino, you understand this. If not, you'll understand it soon. Okay? So this is not only the microprocessor, it's also usually the electronics for a drive. A simple drive system would be a relay. And the mechanical relays are a little bit antiquated and imprecise. So today we're using a lot more electronic relays and amplifiers and things that are semiconductors. Okay. Then there's the executive mechanisms and the actuators, the things that are actually going to do the motion. Okay. There's sensors that acquire data, okay, and communicate with the microprocessor and the drives. And then finally there's the electrical, basically the power sources here, okay, that drive all this and make it work. Now, that's not all there is to most mechatronic systems. There can also be, of course, you've got to get power into it, but there's also communication lines, so it can communicate with the outside world. So these are the common elements of a mechatronic system. Now, I forgot to update this. I apologize. This is something we're not going to use this semester. It was kind of nice. It's a basic stamp development board. It's got a lot of peripherals integrated into it, but Anderson doesn't have these, neither does Columbus, so we're not going to use them this semester. I think it'll be good, because I'm gonna have you guys use breadboard and make some of the things that are normally on here that are already built. It's easy circuits, I'll show you how to do it. But we're gonna use the Arduino instead. The Arduino is actually a lot faster and a lot more powerful than the basic stamp we used to use in this class. So the slide is somewhat obsolete. Okay, any questions at this point? Well, you probably took this class because it sounds interesting, okay? And so what I'd like you to do is help me think of projects that you would like to accomplish. I'll tell you some of my ideas, but I'm not married to them. And you know, if you think of something and you want to do it, that's fine. We can do it. Anybody ever seen this game? I was just introduced to it about a year ago. Some students had seen it and wanted to build something like it in controls class. And I let them attempt it. They didn't ever succeed. But it's kind of a neat game. There's two joysticks on either side. They don't go side to side, they both go up and down. And basically you just control a bar. This joystick makes this side of the bar go up and down, this joystick makes this side go up and down. And you just have this, it doesn't show it in either one of these, but there's a ball that rides on this, this rail. Of course, if you tilt it this way, the ball rolls to the left, tilt it to the right, the ball rolls to the right. And your goal is to put the ball into the hole that's lit. There's also a line around each hole that is your target so that you know which one you're aiming for. And you put it in hole 1, the next ball goes into hole 2, hole 3, hole 4. And it gets harder as you go along because not only are there more and more holes to work your way around, but they get closer and closer together as you go towards the top. So it's a fairly difficult game. The control is not all that precise, and the ball is fairly sensitive to any angle. It'll roll pretty quickly and get out of control pretty easily. So I played the game. There's actually, if you ever go to Rec Bar in, I think it's J-Town. If you ever go there, they've got one of these. You can try your hand at it if you wish. I really enjoyed it because there's no time limit, so you could really play with it and, you know, have fun. But I guess I'm kind of weird too. I thought it would be cool if we made an Arduino control game like this and play it. So that's one potential project that I think would be interesting. Another potential project, someone gave me this, I don't know if you call it a magazine or whatever it is, but it's basically just how to build a fairly high-powered telescope for a fairly low price. Okay. Now, why would we want to build a telescope? Well, I also learned that you can actually see the International Space Station with a pair of binoculars. Apparently it's basically just a little dot, a little white dot, but you can see it. Well, that's not good enough. I want to see features, right? I want to see what it really looks like. Well, if we have a high-powered telescope and we know where to point it, why couldn't we look at the International Space Station and see it? I think that'd be cool. But, of course, once you get into higher and higher magnification, you need something that can track it, right? So the other idea is, why don't we build a tracking system to track the International Space Station so we could look through a telescope lens and just see it as it traverses across the sky. I think that would be really cool. We should be able to get an idea of where in the sky it will be at what times, so we can point our telescope, maybe a low-powered optic, in that general direction. Use a pixie cam, which we have plenty of. We can actually share pixie cams with Columbus and Anderson if we try to take this on. But the pixie cam is really good at detecting color. So it could, you know, given a night sky, black with a white dot, it could probably pick it out pretty easily. And then that would give us an idea, because it could tell us where in the sky it is more precisely. And then we could use precision mechanical actuators to point the telescope, the high-powered telescope, right at that point. So we don't have to do anything, we just look through the lens and see it. Maybe it'd be even cooler, rather than having a lens, maybe we could hook up a video camera to it and put it on YouTube or something. I don't know. Get our 15 minutes of fame, right? And then probably be shut down when the military says, why are you tracking ISS? Anyway, that's another idea that I think would be really fun and really interesting. This one, the problem with this one is there would be some nighttime required, right? We probably want to get the system working, you know, find a room somewhere that's dark where we can put some black paper on the wall and a little white light or something and get it working that way. But of course we want to test it out on the real thing sometime. So that's one downfall of that project, but I think it would be very interesting. And there may be something we can do. I don't know if you guys have been over to Louisville. There's of course you have, but there's a astronomical society or something over there. I don't remember what they call themselves, but I was over at the walking bridge one night, and they had a telescope set up, and they would let the public come and look at Saturn. It was really cool.
because you could see the rings around it, and I'd never seen it before in person, you know. So I thought, wow, this is really neat. So there may be something where we could contact them, tell them what we're trying to do, and maybe they either would have a telescope we could use, or maybe some expertise that we could, you know, bum off of them. Maybe expertise about how this, you know, how you track something like that. I don't know. So there may be something we could interact with them for. And then this is necessity is the mother of invention, right? So I've got this camera here, and I'd really like for it to track me automatically as I move around, because I don't like being constrained to this area next to this screen. I like to go and write on the board. In fact, I would have already to describe better the product that I was building for Grody. But I'm stuck with this camera in one direction, and so there actually are commercial systems. And I don't know if the lecturer or person talking wears something special, or if I don't know how it works, but it will actually move the camera around. There's a demo video that I posted on Blackboard. So we could build something like that too. We can get cameras that have control, or we could take my camera and build a gimbal for it. That wouldn't be all that difficult. But then how do we control it? So it's actually very similar to the telescope problem. But with a telescope problem, we'd have very fine adjustments, whereas this would be fairly coarse movements. So anyway, those are my ideas for a project. Here's some other wild and crazy ideas. I don't know if we could really do this, but have any of you ever ridden on an Orbitron? You know what it's like? Well, it's basically 3 rings, and it allows you to rotate in any direction. Okay. Have you ever played with a space ball? You know what a space ball is? Well, a lot of people don't. A lot of people think that this is a trackball that rolls. It isn't. I did a lot of CAD work for Amatrol when I was there as a design engineer. And I discovered this about halfway through and thoroughly loved it. In CAD, in all CAD programs, unless you program keys on the keyboard, which most people do, you have to go and click on an icon to zoom in or to rotate or whatever, you know, the model you're working on. This is really cool because it's like having a hold of the object on the screen. See, the way this thing works, you can push and pull in any direction, and you can twist in about any axis. Okay? It's like having your hand on the CAD model and moving it around on screen while you work on it with your other hand with the mouse. It's really beneficial. It's actually really increased my productivity, and I really liked it. But I thought it would be amazing. I'll tell you the rest of the story. I wanted one of these, and I looked on eBay several years ago and found somebody that was selling a lot of like 20 of them or so. So I thought, my entrepreneur side came out, and I bought them all and then sold them one at a time on eBay for a profit. Ended up getting basically 3 or 4 of these for free. That's what happened. But I thought, you know, it'd be awesome to mount one of these on an Orbitron so that the user sitting in the seat could actually control which way they move, you know? So another thing that I think would be fun. That would also be mechatronic. I'll tell you a little bit about the projects we've ran in this class in the past. This is actually one of them. We didn't build this, but we built a self-balancing Arduino-based robot. And that was pretty interesting. Never worked quite right. This one's beautiful. If you look at the video of it, I've got one posted on Blackboard. But our robot was constantly moving back and forth, but it did stay upright. And so we called it a success and moved on. It was kind of a secondary small project. So we've done that in the past. I don't know that I'd really want to do it again, but it could be interesting. One thing that I've always wanted to do is have robots walking around or rolling around when students or prospective students are here, asking them what room they're trying to get to and actually acting as a host to take people to various classrooms. I think that would be really cool. Of course, we wouldn't be able to get to that level in this class, but we could possibly build a self-balancing robot that's a little bit better than what we made last time I taught the course, which was about a year ago. So we could try that if you're interested in it. In the past, the first time I taught the course, I bought a pinball machine. Now, a pinball machine is an electromechanical device. It's not a mechatronic system. And I really wasn't sure what we were going to do with it. I just knew that if I brought a pinball machine into class, I would get the students' attention. And there must be something we could do with it that would be mechatronic. So I brought it into the class, and I actually asked the students, I said, okay guys, what are we going to do with this? And we went through a whole brainstorming exercise. And it was good because, I don't know if you know much about brainstorming, but in brainstorming, you're not allowed to critique. We're all engineers, at least we're all bent that way, right? We're all great at critiquing. Well, that's fine, there's a time and a place for it, but when you're trying to generate ideas, you should not critique anything. All wild and crazy ideas are accepted, they're fine. Okay? In fact, the game had a knights in shining armor theme. I didn't go with anything too risque. This is still school after all.
But I brought it into the classroom, and it was, you know, just a knight with a sword or whatever on the backlight. And we were brainstorming, and one of the guys said, well, it'd be cool if you hit a certain target that there'd be a gun on the side, you know, a toy gun. You pull it out, it's a quick draw, and you shoot a target and get some points that way. So we wrote that down as an idea. Well, that idea evolved into, well, wait a second, this is a knights in shining armor theme. What about if it was a sword in the stone, see? And you struggle to pull this sword out when you hit a certain target. And if you get it out, you get more points. Okay? So that's how the idea could evolve a little bit and change and be something that is actually useful. Well, what we finally decided to do, we finally decided it wasn't fair. You know, you go to the arcade, if you can find one these days, and the video arcades are playing themselves, right? The character starts running along on the platform and dies, and you think, oh, I can do better than that. So you put your quarter in and you play, right? So that's the way they advertise. Pinball machines don't do that. Pinball machines just flash, right? You never see the ball in the play field. And we thought, that's not fair. Wouldn't it be cool if pinball machines could play themselves so that you say, wow, that looks like fun. I want to do that, you know? So we made the pinball machine play itself. And the way we made it mechatronic, the precision mechanical aspect, we thought we built a device that would retract the plunger, and the goal was to make the plunger retract to very precise amounts, which we succeeded in doing, so that when we shot the ball into the playfield, ideally we would find a path, an amount of speed or whatever, that would hit a lot of targets on the way down. That was part of our strategy for maximizing our score. It turned out it really didn't matter where you shot the ball into the playfield, you got about the same result. Okay, so, but we did end up having a mechatronic system because we could control the position of the plunger very precisely. And I'll have to post some videos. I don't think I have any of those posted on the Blackboard site. I just realized that. So I'll have to post some of those so you can see what we did. Anyway, so that's what we did the first semester. The next semester I used the machine again, and we were trying to figure out what to do because kind of the cool project had already been discovered. And we thought, you know what, it is really not fair that you ever measure the distance between the flippers when they're extended and the diameter of the ball? The diameter of the ball is smaller than the distance between the flippers. And of course the goal is you got to be good at bumping the machine enough to not trigger the tilt sensor, but to get the ball over to the, you know, that's kind of what you have to do, right? But we thought, you know what, it's just not fair. We want to be honest, upstanding people and play this game with dignity, right? So it's not fair. So what we're going to do is very precisely locate a sensor so that when the ball comes down, if it's close enough to a plunger, it won't trigger the sensor. But if it's in that spot, that unfair spot right in between, we're going to use a puff of air and push it back into the playfield. That's what we did. So we had this little jet of air to push the ball back when we detected the condition. How was it mechatronic? I don't remember. We did something else. But anyway, those are the projects that I've run in the past. There were a couple times I did not teach the course, and you guys may remember Michael Dobrik. He taught the course a couple times. And one of the projects he ran was an air hockey table, not a full size, but one of those cheap ones you can get at Walmart, with stepper motors on each end that moved essentially paddles back and forth to make the air hockey machine play. Okay, so you had a computer player on one end, you could play on the other.
So it was Pong.
It was essentially Pong. Yeah, exactly. But in real life. So that's another project we just been running. While we're talking about it, do you guys have any ideas? Anything you'd like to build? Any interests? No fan? Okay, well, give us some thought. If you come up with something, you know, remember that it basically has to be something where it's computer controlled, and then we have to have some precise mechanical actuator, okay? So that's basically the only requirement. Of course, we have to be able to program it. That's important too. But hopefully there's something that will pique your interest. Okay, well, not every electromechanical system is mechatronic. Some electromechanical systems have some elements of a mechatronic system, but not all, and therefore are not mechatronic. To that end, I've brought in two devices today. I brought in a microwave and an inkjet printer. What we're going to do is tear them apart. And I really don't care how careful you are as you tear them apart. I'll show you components as we go. I'm going to pause the camera in just a minute because the Anderson students are doing the same thing in their lab on Wednesday. But once the machines are apart, well, I'll take the camera off, we'll go over and point out a few things. Okay? We're going to take them apart. Now I want you to think about which one of these devices is actually mechatronic. I'll give you a hint. One is and one is not. I want you to figure out whether the microwave or the inkjet printers are actually mechatronic and why you think it's so. Okay?
I also want you to recognize any elements of a mechatronic system in both the inkjet printer and the microwave. And this is the first and only time I will have you write a report. Okay, so it'll be a 2-page report on why one is mechatronic and the other is not. So I'm sorry about the writing, but it's something you need to practice. So before we start this, what do you think? What do you think about the two? Which one seems more mysterious to you, the inkjet printer or the microwave? Yeah.
Inkjet printer.
Think-
It's mechatronic.
You think the inkjet printer is mechatronic? Okay, but which one seems a little more mysterious to you, the way it works?
Inkjet printer.
The inkjet printer? Okay. To me, it was the microwave. It seems almost magical, you know. But I think there's probably deeper physics in the microwave. But I won't give it away yet. We have an opinion that it's the inkjet printer that's mechatronic. We'll see. We have to back that idea up with fact, right? With whether or not the elements are present in each one of these. Well, I will stop talking and we will start working.